Okay, we're going to talk about Taylor series and Maclaurin series, which I'll just abbreviate to T series and M series. Okay, so what are these things about? So we've learned about the great advantage we have if we're able to represent a function as a power series. And we've learned about some particular functions that we can actually do that for. Now we're going to learn about, in general, how we can represent a function as a power series, how we can find it, and whether or not we can really do it, whether or not we can really use, or whether or not we actually have a representation of a function as a power series. So let us begin. So let's imagine to begin with that we actually do have a power series, and let's try and figure out stuff about it. So given f, suppose, we can write f as a power series in this way. So we write f of x is the sum from k equals 0 to infinity, ck, x minus a to the k. And let's write out the first few terms just to get some impression what that is. That's c0, c1, x minus a, c2, x minus a squared, that's c3, x minus a to the 3, and so on and so on and so on. Right? So we would like to know what are these coefficients. So this is our question. And it turns out we can figure that out without too much difficulty. So the first observation to make is that if we just stick in x equals a, all of these terms here will just cancel out, and we'll straight away find out what c0 is. So if x is equal to a, then we find that c0 is just f of a. Cool. So that's progress. What about if we want to find the other ones? Well, the natural thing to do at this point is just to differentiate the expression that'll kill this constant term, and we'll get c1 as a constant term after we do that. So let's write that out. So if we take the derivative, so f prime of x, the constant term just drops, and what are we going to get? We're going to get c1, or just c1 by itself. And then 2c2, x minus a, plus 3c3, x minus a squared, plus 4c4, x minus a to the 3, and so on like this. Right? So, same procedure. If we stick in x equals a, then we find a way, straight away, that f prime of a is equal to c1. Cool. And then we do this again. We differentiate again. F double prime of x, the constant term drops. And now the constant term becomes 2c2. And here we're going to have 3 times 2 c3 x minus a. And then here we're going to have 4 times 3 c4 x minus a squared, and so on. Stick in this, and we find straight away that f double prime of a equals 2c2. Let's just do it one more time. Differentiate this thing. This constant term drops, and we're going to get f double prime x, and the constant term will then be 3 times 2 c3. Then here we're going to have 4 times 3 times 2 c4 x minus a, and then these other terms here, and then sticking in there should be a here. We're going to have f, the derivative of a equals 3 times 2 C3 Okay? And you can see how this is going to go. So if we keep doing this stuff, what are we going to find? We're going to find that the kth derivative at a will be equal to k factorial times ck, which is equivalent to saying that ck is equal to, and we have an explicit expression for our coefficients. Cool. So, if the power series does represent the function, if this is true for some range of x between a minus r and a plus r, for any r which is positive no matter how small, then we can do this stuff because we can just differentiate term by term through the power series, and we explicitly know what the power series have to be. So if the power series exists at all, then we write it down. So if power series exists, then this is the power series. It is the sum, k equals 0 to infinity, of the kth derivative at a over k factorial and x minus a to the k. And the first terms, if we write them out, are what? So it's going to be f of a plus f prime of a x minus a and double prime of 2 x minus a squared, and so on and so on. And what is, or what should hopefully be quite immediate and interesting to you, is that these first two terms here are exactly the expression for the tangent line, right? Which is something that already was talked about. But now we explicitly see the expression for the tangent line here in the first two terms of the Taylor series. Okay, cool. Let's calculate a specific example and see what it tells us. So, let's do the following example. Suppose we have f of x equals e to the x, then any order of derivative is again e to the x. All right? So, if we try and create the power series centered around 0, what will it be? So the power series is how it has coefficients given by the kth derivative at 0, which in this case would just be e to the 0, which is just 1. Right? So just putting in the formula, the sum k is equal to 0 to infinity of the kth derivative at 0 over k factorial times x minus a to the k. This time a is 0, so this is just x to the k. Then this is what we get. Infinity. Cool. All right. So, key point. This is not yet saying that this power series represents e to the x. That is true, but we'll talk about that later. All that we know is that this expression, if it does represent the power series, start again. All we know is that if we do have a power series representing a function, then the coefficients have to be given by this expression. Okay? We don't yet know that this actually does represent the power series. That is an unknown thing. Damn it, say that again. We don't yet know that e to the x actually has a power series yet. That is an unknown thing. Okay? All right, so let's try and figure out about the radius of convergence of this power series. So again, we don't know that this thing actually represents e to the x yet. So let me write this down. So don't know if this is its power series. Yet. Okay. All we know is that if it did have a power series, then it would have to be of this form. Okay. However, now that we have a power series of this form, let's ask ourselves what's the radius of convergence of this. So well, we're just going to use what we know how to do, right? We're going to use the ratio test. So we'll let ak be x to the k over k factorial, and then absolute value of ak plus 1 over ak will just be x over k plus 1, which tends to 0 as k tends to infinity. So no matter what choice of x, since this thing is always going to go to 0, this power series converges everywhere the radius of convergence is infinity. So the radius of convergence is infinity. Cool. All right. So that's just to get a flavor of how we can calculate these expressions here. Let us further discuss what this can mean on this example. So if we draw a graph of e to the x, let's put it here. Not the best graph. Okay, not perfect still. Well, what's the crudest possible approximation we could do around 0? Well, the crudest possible approximation is just to take the value of the function at 0, which is 1, right? And if we did that, we get this, yeah? And a slightly better approximation, or a much better approximation, is to take the tangent line. And if we take the tangent line, then it is this line right here. Right? And if we notice our power series expansion, so let's call this thing star and write out the first few terms. So star, what is it? So when k is equal to 0, it's just 1, right? Because 0 factorial is 1, so it's 1. And then when k equals 1, it's x. And when k is equal to 2, equals x squared over 2, and then x to the 3 over 3, and then so on, right? And you notice that the 0th order approximation, which is what I mean by if we just take the first constant term with no derivative at all, it's just this function, right? So this is this function right here. Say y equals x, y equals 1. And then a slightly better approximation is when we take the first two terms, and that's just the tangent line. So that's the tangent line. Right? So this is just x plus 1, that's the tangent line. And if we considered the first three terms, I should put some dots here. If we put the first three terms, then we'll be adding this quadratic expression here, which would somehow bend things a little bit more. So kind of look like this, which does an even better approximation, right? And gradually we'll get a better and better approximation by considering more and more of these terms. right? And that motivates this next definition I'm about to give, which is the nth order Taylor polynomial. So we define to be what happens when we sum from k equals 0 up to n. Okay, so in particular, T1 of x is equal to which is exactly the tangent line. Okay, so this thing here was T0, and this thing here was T1, and this pink thing that starts to curl and approximate better is T2. Every additional term we take brings it closer to the actual function. Okay, cool. Okay, now let's discuss the question about the question of when a function actually has a Taylor series. To do this, we have to define something else. So let n of x be the difference between the function itself and the nth ordered Taylor polynomial. Okay, so what does it mean for a series to converge? It means that the partial sums tend to a limit, right? So for a power series to converge, it means that the nth ordered Taylor series tends to some particular limit for each x, and that limit has to equal the function itself, right? So f has a power series on some interval a minus r, a plus r, is equivalent to the limit as n tends to infinity of Tn of x equals 0 for, oops, not Tn, Rn. For all x in between this interval. Okay, so we'd like to understand when this thing actually happens, when the remainder actually tends to 0. And to explain this, we have to actually state a theorem which is a little bit technical, and I'll try and make it more palatable or more understandable. It's Taylor's inequality. So theorem. What does that say? It says that if we have that the kth plus 1th derivative, the absolute value, is less than or equal to m for all x which is between this interval a minus r. Oops. And a plus r, then n of x is less than equal to m, absolute value of x minus a to the n plus 1 over n plus 1 factorial. Okay, so this looks like a little bit of an intimidating expression. And in this particular case, this is a real theorem. It's not only a real theorem, but it's a theorem that is not that easy to explain. Even in the courses where it is explained, this is a definitely non-trivial theorem. However, it isn't hard to believe. And let me try and motivate it. So recall, if we had an alternating series S, which is the sum from k equals 0 to infinity, minus 1 to the k bk, and we took the Sn partial sum, the sum from k equals 0 up to n, minus 1 to the k bk, then we have that the difference between the Sn partial sum and the actual sum is less than the size of the Bn plus 1 size step, right? And there's a very simple natural geometrical reason for that, right? We've talked about a number of times. Okay, look at this expression here. Well, the n plus 1th term of the power series is not one word. Is what? It is the nth plus 1th derivative applied to a over n plus 1 factorial x minus a to the n plus 1, right? Okay, so if the same thing that is true for alternating series was true of power series, then we could bound the difference between the nth partial sum and the actual answer, the actual sum, by this term, right? But that isn't true. That's not quite strong enough. However, something very similar is true if instead of having this nth plus 1th derivative applied to a, if we take the supremum of the nth plus 1th derivative applied to any point inside the interval from a minus r to a plus r, then it's actually true. So the trick is to replace this thing by m. Okay? So putting this thing here, we put m here. And m is clearly bigger than this quantity because m is the supremum of the nth plus 1th derivative over the interval a minus r to a plus r. And that looks a lot like a k, but it should be an n. Right? So this expression kind of should seem natural, right? It's not a million miles away from what we've learned from alternating series. And in fact, the reason it's true is not a million miles away either, because a power series, in a sense, is something which has a kind of delicate flavor like an alternating series. As you range x over the interval a minus r to a plus r, then it feels a bit like an alternating series. I don't have a better word than that. Okay, so this is one of the few times when I'm not going to be able to draw you a picture as to why this is true, and you're going to have to semi-memorize this fact. However, I want you to use this analogy to understand or to remember why it's true. And later in a high-level course, you can see exactly why it's true. Okay. All right. So if we are able to establish that for some range of x between whatever a minus r and a plus r, as n goes to infinity, this quantity here goes down to 0. Right? If as n goes to infinity, no matter what x is between a minus r and a plus r, this goes down to 0, then that would say that the remainders go down to 0, which means that we actually do have a power series over that interval. And that is what we're going to see next for this function e to the x. So let's put it over here. All right, so if we consider e to the x, then we know all the derivatives, right? Any order of derivative, again, is just e to the x. Yeah? So take any d which is bigger than 0. Could be 1, could be 1,000, could be 1,000,000, whatever. And we're going to consider the convergence of the Taylor polynomial, the nth order Taylor polynomial, to e to the x over the interval minus d to d. So we consider minus d to d. Right? So what is going to happen? Well, according to Taylor's theorem, then we have that the remainder is less than the supremum of the kth order derivative. The supremum is a fancy word for saying the maximum. Sorry, the kth plus 1th order derivative. This k x should not be this k. It is the supremum of the kth plus 1th order derivative over the interval minus d to d, right? And what's that supremum going to be? Well, the function is e to the x, so the supremum is going to occur at d, right? So let's draw a quick picture. So this is d minus d. This is what e to the x is doing, so obviously the supremum occurs here. So for this m, what we're actually going to have is just e to the d, right? And then what about this x minus a 0 here? So this will just be d to the n plus 1. And underneath we have n plus 1 factorial, right? So the issue is, does this expression tend down to 0? And hopefully you guys notice quickly that it does, because d is just fixed. We just took it to be some number. And then if we look at this expression, we have, this is like e to the d, and then we have d times d times d, and so on, n plus 1 times. And on the bottom we have n plus 1 times n minus 1, and so on all the way down to 1, right? And these guys are way bigger than the d, no matter what d is, as n goes to infinity. So this is indeed going to go down to 0. And if you are still not happy about this, then, for example, you can just take the ratio test, and you'll see that this thing is going to form a converging series, and therefore these terms do have to tend to 0. But this should be fairly convincing. So this thing goes to 0 as n goes to infinity. So in particular, the limit, well, I'm just saying exactly the same thing, the limit as n goes to infinity of r to the n to the x equals 0 for x between a minus r and a plus r. Which means, put it over here, that this function e to the x actually is equal to its Taylor series. on minus d to d, but d was completely arbitrary. D was any number, so it's actually true for the whole R. Okay. All right. So because of Taylor's inequality, we have this function actually does have a Taylor series. Right? So when it comes to integrating, differentiating, scalar multiplying or multiplying by x or anything like this function, we can deal instead with the power series and have a much simpler life. Cool. And that is the start of being able to represent functions by a power series. So e to the x is the first one we can do. Let's find another one. Let's do another example. So sine of x has a power series. Okay, I should start to call them now Taylor series or Maclaurin series. And I haven't told you the difference. So a Taylor series is a Maclaurin series, except it's centered around A. Or another way to say it is that Maclaurin series is a Taylor series when A is equal to 0. So show that A has a Maclaurin series, so an M series, which means we are going to find the power series centered around 0, just as we did in the previous example. So let us get to work on this. So solution. All right, so we are going to have to show that there actually is a Maclaurin series by showing that Taylor's inequality holds true, and that means we're going to have to calculate some derivatives. So let's start with that. Let's, for convenience, write f of x equals sine of x, and let's start to differentiate. Oops. I get perfectionistic here. And then it's just going to repeat, right? And we're going to do this at 0, so let's put this bar right here, or this line right here, and let's write when we have a 0. So f of 0 is 0, f prime of 0 is going to be 1 here, f double prime of 0 is 0, the third derivative at 0 is minus 1, and then the fourth derivative is 0. Okay, so we're going to have this 0, 1, 0, minus 1, 0 pattern repeating. Okay, and we can actually write down the series that would be the Maclaurin series if we knew that the function had a Maclaurin series just from doing this. But first, let us check that it actually does have a Maclaurin series. Or perhaps we should actually first write it down. Since we just did this work, actually let's first write it down. So if sine of x had an M series, then it would be what? So the general formula is this: the sum from k equals 0 to infinity, the kth order derivative at 0 over k factorial x to the k, and this is what we figured out has to be the derivatives at 0. So we notice that all the even powers are going to be 0, and we just have the odd powers, and then they're going to alternate from plus and minus, right? So we're going to write this as the sum from n equals 0 to infinity, and we can write odd numbers as 2n plus 1, right? At 0, because, and then x to the n plus 1, first step. And then, now that we know we just have the odd numbers, we just got to see, we've got to pick up the alternating structure, right? So when n is equal to 0, then we get the first derivative, which gives us 1. When n equals 1, we get the third derivative, which gives us minus 1, right? So then now we know that this is the sum from n equals 0 to infinity. It's going to be minus 1 to the n, x to the n plus 1, over 2n plus 1 factorial. So again, if sine actually had a Maclaurin series, that would have to be the Maclaurin series. But we don't yet know that this thing is equal to sine. And to do that, we need to use Taylor's inequality. So let me write that. So to check if sine has an M series, we use Taylor. Okay, so what will that involve? So Taylor's inequality is that the remainder, n at x, which is the difference between the nth order Taylor polynomial and the function itself, is less than m, which is the supremum of the nth plus 1th derivative of whatever interval we're considering, n plus 1 factorial, and then just absolute value of x to the n plus 1. Okay, so I'll consider interval from, say, minus d to d, so and put it over here. What happens then, since the nth plus 1th derivative of sine will either be plus or minus sine or cosine, depending on what n actually is, its absolute value in any case, no matter what x is always less than 1. Right? So our m, we can just take to be 1. Right? So that means that our n of x is less than, so we're doing the interval from minus d to d, so we're going to have d to the n plus 1 here over n plus 1 factorial. And just as we've seen before, as n goes to infinity, this goes down to 0. So the limit as n goes to infinity of the Rn of x remainder is equal to 0. So sine does have a max series on the interval minus d to d, but d was arbitrary, so it's actually got a max series for the whole of R. Okay, since it does have a max series, by this fact that we know the coefficients, the max series has to be equal to this. So to conclude, we know that sine has a Maclaurin series, and it's exactly given by this. So let me put that down here on the bottom. Let's change color. So sine of x is equal to the sum from k equals 0 to infinity minus 1 to the k x to the k, x to the 2k plus 1 over 2k plus 1 factorial. Cool. So just as with the exponential function, if we want to do any stuff with this thing, I'm going to integrate, differentiate, multiply it by x to the 3 or anything, we can deal with this Taylor, this Maclaurin series instead, this power series. And one of the cool things is if we do multiply it by x squared, then that still will be a power series because we just multiplied the x squared through. So just as we saw from the last time, once you have a power series, you can do a fair amount of stuff and still have a power series. You can differentiate, you can integrate, you can multiply by powers of x. So not only does this give sign, but it gives a whole range of things, a whole range of functions that we can represent with a power series that we build out of sign. Cool. All right, let's do another example. Now that we know about the difference between Taylor and Maclaurin series, maybe I'll write it down. So T series is centered around A, and then M series, Maclaurin series, centered around 0. Okay. We are going to calculate a Taylor series, i.e. something which is not centered around 0. And this is our exercise. So, example, calculate the T series of e to the x around a equals 2. Okay, solution. So let's write down the formula just to warm us up to get a feeling what we're doing. So it turns out, for exactly the same reasons that this guy has a Maclaurin series, it has a Taylor series. So we're just going to take it as a given fact that it actually does have a Taylor series. In fact, the question implies it because it just says calculate the Taylor series. So we're not going to have to worry about Taylor's inequality and showing that it actually does have one. It's true, we'll assume it. So if it did have one, then what would we know? We would know that, let's actually write as f, make better notation, that if we let f of x be e to the x, then the Taylor series would be what? It would be this, right? It would be the sum from k equals 0 to infinity, the kth derivative applied to a, because we're doing this around a, divided by k factorial, x minus a to the k. So now we're going to have to calculate the derivatives at a particular point, in this case 2. So I could have put 2 right in here. A equals 2 in this case. So the derivative, any order of derivative of e to the x, of course, is just e to the x. So the kth order derivative at 2 is e to the 2, and that's it. That's all the work we have to do, because now we just plug it in directly into the formula. So let's write it as e to the x. Right? So e to the x is the sum from k equals 0 to infinity, e to the 2 over k factorial, x minus 2 to the k. Pretty simple, no? Surprisingly simple form. All right, so that's if we want to take the Taylor series instead of the Maclaurin series. Often it can be a lot more tricky than that, but that's how you do it in every case. It's exactly the same story, except now we're calculating the derivatives at the center of the series. And we're using this formula as x minus the center to the power k. Okay. There are some standard series that we expect you to know and that you'll be examined on. In fact, you probably know them already. If you've done a bit of calculus, perhaps you've memorized them. But as I keep saying, we are not interested in memorizing anything in this course. the best way to do this, the best way to have these in mind is to work them out. So I've already done e to the x and I've done sine. You can do cosine in exactly the same way. You can do all these guys I'm about to list in the same way. But these is just a short list. These are the basic ones we'd expect you to know. So this is the first one. And this we know just because it's the formula for the geometric series. Let's put it over here. This is 1. The next one, I've written it lots of times. Let's write it again, e to the x. It's this thing. The next guy is sine. Let's put that as 3, which we've also already done. So sine of x equals the sum equals 0 to infinity minus 1. It's the k, x to the 2, k plus 1 over 2k plus 1 factorial. The next guy is the cosine. That's, what's that, 4. And exactly the same way we calculated this, we can find this thing out. This is minus 1 to the k, x to the 2k over 2k factorial. The next basic one is, oops, put the number in 5, arctan. Okay. And arctan of x, actually we calculated not by simply, we're not going to calculate it by taking one after the other derivatives. Arctan we calculated in the last class, or in the last lecture, simply because we can turn this into the algebraic form 1 over 1 minus x, or morally 1 over 1 minus x, because the derivative of this guy is 1 over 1 plus x squared, which is 1 over 1 minus x squared, which we can power series expand, and then we can take the antiderivative and get it back. And I think we even did it in that class. But in any case, this is the series that we have. And this is like a kind of a cool exercise, or a free response question is to ask a student to calculate the Maclaurin series of this, because if you don't remember this fact that you can get this from this 1 over 1 minus x formula by first differentiating, expanding, and then integrating, then you would be stuck trying to differentiate this function over and over again, and that would be a very painful experience. And you could actually, calculate the first however many times you want, and maybe you'd pick up the pattern if you kept doing it, but it would be an awful thing to do. So way better to have paid attention in the previous class. All right, so that's another one. And final one is this guy. And this is also a guy that we can do because of the fact it looks, or it can be turned into something in the form 1 over 1 minus x. This time we differentiate. And I think we did this one too. So we start with equals 1 this time to infinity minus 1 to the k minus 1 x to the k over k. So we, in fact, have seen all of these guys before. And the way to know them, the way to get them right, is to have them in mind. Okay, so this leads us to another kind of question that you can see. And I'll put it down here because I need all these formulae. So let's change color to green. Maybe I want the space later. So this is our question. Find the sum of this thing. 1 over 1 times 2 minus 1 over 2 times 2 to the 2 plus 1 over 3 times 2 to the 3 minus 1 over 4 times 2 to the 4, and so on. Okay, so up to this point, I've told you that when you have some explicit series, and it says, and the question is, find the sum, or what is the series, then it can only be one of two things. It can only either be a geometric series, or it can be a telescoping series, because those are the only two things we can explicitly calculate. Okay. Now there's another thing we can do. Now we have another way to explicitly find the answer to some given power series. Okay, not power series, some given series. And that is because of what we've just learned. So I'm going to try and erase some space here without rubbing everything off. I've never tried to do this before. It's not that easy. Okay, let's work in this little space. So, how are we going to do this? Well, what we've just learned is that we have explicit Maclaurin series for various kinds of functions, right? So if we look at this guy and we try and write it as some particular formula, so let's call this thing star. So, what would we do? So we have this 1 over 1 times 2 minus 1 over 2 times 2 to the 2, and we can quickly come up with a pattern, right? So we're going to start with k equals 1 to infinity. We're alternating plus and minus, so we're going to have minus 1 to the k minus 1, or plus 1, it doesn't matter for that thing. And then on the bottom we're going to have k, and then we're going to have 2 to the k. And that recovers all these terms, right? Just to check, so when k equals 1, then we're just going to get 1 over 1 times 2, and then we're going to have minus 1 over 2 times 2 to the 2, and then plus 1 over 3 times 2 to the 3, and that's exactly our guy, right? So this is the right guy. And if we look at that, we can actually write this as the sum from k equals 1 to infinity minus 1 to the k minus 1 over k, and then 1 over 2 to the power k, right? And what we are looking at here, or what we might recognize we're looking at, is an expression where we've put something inside a power series, i.e. this x equals 2 could be what happens if we put, say that again, if we had the power series given by this thing with x to the k and x was equal to 2, we would have this, right? So this is equal to the sum from k equals 1 to infinity minus 1 the k minus 1 over k x to the k with x is a half, right? And then if we look down our list of Maclaurin series, we will find this guy inside the list. So it's not this, 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 it is this guy, right? It is this guy, yeah? So for x equals a half, this expression is this expression, and this is nothing other than log of 1 plus x. Okay, so this is actually just log of 1 plus a half, so it's log of 3 over 2. So we explicitly have what this series is. It is equal to log of 3 over 2. All right, so we have a third way to explicitly find some given series. So now you have to keep in your mind that when you're asked the question, find the sum of or what is, then geometric series or telescoping series, or it is just the result of sticking some number inside a well-known Maclaurin series. And that's why you need to know these basic Maclaurin series. So you will see homework exercises like this. You might have exam questions like this. You're going to have to keep your wits around you, look at an expression like this and think, okay, how could I recover this? And hopefully your thought process will go, all right, it's not a geometric series. It looks a bit like a geometric series except for these terms here. It's not a telescoping series. There's no n minus n plus 1 type structure here. So what else could it be? It's got to be a well-known Maclaurin series. So you say, okay, let me write this out. See, it's something like this. It'll be some coefficient in front of some number to the power k, and then just stick in x is that number, and then write it like a power series, and then think back what power series are going to match this. So this isn't hard. It's just that you have to keep another thing in mind. In fact, it's kind of easy. It's kind of a giveaway when you're asked to find the sum of, because it can only be these three things, and they're completely different things, right? They're completely different series in each case. So you will quickly identify what kind of series it has to be, and then you'll find the method. So these questions shouldn't be too difficult for you. Okay, that's it.